So today what we will do is that we'll start off from where we left last time and now move on to understanding swimming of microorganisms. Okay. That's sort of our upper goal today. And the idea would be to talk about some general principles and general ideas that govern the locomotion of microorganisms in fluids. And then we will try to do a specific example and work it out in detail. Okay. So just a quick recap of what we did last time. We said that in the low Reynolds number regime, when things are either at the scales of microns, as for microorganisms, or the fluid is extremely viscous, or things are moving very slowly, or it could be combinations of all these things, the governing equations of fluid flows are the incompressible Stokes equation. Here is the pressure, U is our velocity field, and this is assumed to be a constant density incompressible field. That's the divergence of velocity 0. So that's our governing equations of the problem. And then what we spent a lot of time doing is that we went through a number of properties of these equations. Okay. Let me just go over them quickly once more. So first is these equations are linear, right? So these PDEs are linear. So if you have two solutions, you can add them and get another solution. So these are all linear PDEs. That was one thing. The second thing, which is more subtle, is that these equations do not have any time. There is no explicit time showing up in these equations. And what that means that we realized last time is that everything in these flows are driven by boundaries. So you have flows, you have velocities, things move, fluid particles move only if you have driving coming from boundaries. So if something is moving, things will move in the fluid, otherwise it won't. Okay. So that's the boundary driven part, or mathematically these are called boundary value problems. So consequence of sort of these two taken together was that the forces are proportional to velocity. Okay. So this is again, we did through an example. We looked at the sedimenting sphere problem, which you guys did in school. And we pointed out that the drag force acting on the sphere as it sediments is proportional to its velocity. Okay. And in general, forces are proportional to velocity. Forces are linearly related to velocity. And a linear relationship between two vectors would mean that there is a matrix mapping these two vectors. And this matrix R we called as the resistance matrix. Okay? And of course, for sphere, this was simply an identity matrix times a constant, which depend on the geometry of the object. And we will see today that this need not be the case for general objects. And it could indeed be a matrix, and we'll see what are the implications of that. Yes?
If there is a body force or something doing that, like gravity or something.
So let me come back to the question. I will answer this. Okay. And the final property was the property of reversibility. Okay. And the way we illustrated this is that we thought of this problem of a moving sphere. And we said that, let's take his example, like he mentioned, that there is a sphere that's sedimenting and there is gravity acting on it. And that's why it's falling down. And we said that if we just reverse the direction of the force, then all the motion of the fluid will be immediately reversed. Okay. The patterns of the flow won't change, only its magnitude will change if I change the magnitude of forcing. Okay? And that's this kinematic reversibility idea, and it doesn't matter time. There is no time. As a result, the time scale over which this switches is essentially instantaneous. Okay? So now coming back to his question, is that what is this force? Is this a gravity? Is this a drag? So let me just answer this. Remember, whenever you have a particle moving in any fluid or anywhere, you have essentially Newton's law. So the way I would write it is that there is some external force acting on a particle. In this case, it's gravity. If it's a charged sphere, you apply an electric field, it could be some other forces. But this is some external force that's driving the sphere. And then there are drag forces coming from the fluid. And this is equal to the mass of the particle times its acceleration. This is our governing equation. Now what we showed last time is that this term over here is really subdominant in the problems of Stokes equations, right? So this is the way we illustrated this, is we said that suppose there is a bacteria that's moving and it now stops swimming. So it has inertia. And how far will it go before it stops? And we estimated the distance it goes is 1 nanometer. So effectively it doesn't move. So these terms are really small compared to whatever you have on the left hand side of the problem. So what we said is that let's drop this term and we will say that this is roughly 0. So what this means is that at any instant of time, the drag forces will balance the external forces. So essentially you have this relation, F external equal to negative of F drag, right? Now, which is, if the force is acting in this direction and this guy is moving in this direction, then of course the drag force is going to act in this direction, right? Okay. So if I write this in component terms, right, this is, say I take this to be the z-axis. So my drag force is effectively minus 6 pi mu a times u. So u is in the negative z direction, that's why I have a negative sign, so this is in the plus z direction. And the gravity is of course in the negative z direction, and together they should balance. So which force is this? Well, this could be the external force. If you're writing this for external force, remember to put a plus sign here. If you're writing this for the drag force, remember to put a minus sign here, because the drag force is acting opposite to the direction of the motion. Yes?
But do we need to add a gravity term in the radius?
Okay, that's a good question. So right, if in this problem, you don't need to add it because it's the particle that's getting forced. Suppose the fluid is also getting forced. Suppose there is a vertical, there is gravity and the fluid is also getting forced, then you need to add it. Otherwise, if it is just a particle getting forced, you can think of this problem as there is some velocity u on the particle that's driving the flow. But you are right, in general, these equations should be augmented by the fact that there is some external force. This is force per unit volume acting on the fluid. That's correct. Okay, so we stopped here last time and there were these two puzzles that we are thinking of, and they are related to this property of reversibility. So let's see, did you guys get time or chance to think about these puzzles? Okay, so
Excuse me, sir.
yes.
Sir, actually, I have one question related to that video which you sent by G.I. Taylor.
Yes. Okay, go ahead.
Sir, actually, in one place he actually mentioned that in a particular situation, cavitation bubbles appear. What does that mean actually?
Okay, so cavitation bubble can appear if the pressure goes down. Okay, so if the vapor pressure, so water has a vapor pressure. If the absolute pressure goes down below it, the water can evaporate and you can have formation of bubbles. Okay, and so if you have an equipment, so if you have a turbine and you're operating it, and somehow the pressure has gone down and the water has evaporated and now it's forming bubbles, those are called cavitation bubbles, and they can be very detrimental to the instruments that you're using. That's what's going on there. So if you drop the pressure very, very low, if there's low pressure, you can have cavitation. Cavitation bubbles mean that. So if there is a phase change of the fluid with which you are operating. Okay?
And actually, how is it dangerous to the equipments you are operating?
Well, it depends. If the equipment has a low pressure situation, okay, then you will have that. I mean, it's not necessarily you will always have cavitation. If you operate a fluid in a condition where the absolute pressure has gone down below the vapor pressure, then you will have cavitation. It depends on the context of the problem that you're looking at.
Okay, sir.
Okay. So let's get back to this thing and see what's going to happen, which direction. So let's do this problem first. Which direction is this sphere going to move? There will be no lateral movement. So it will fall straight. So why is that? What sort of is the rough argument? Yes.
Say it move towards the wall.
So say it moved towards the wall. Let's do that experiment. So let's say it moved towards the wall. Yes.
If we now reverse time,
Yes.
it moves away from the wall.
Correct. So if I reverse time, so did everyone follow this argument that let's assume that this is moving towards the wall. Now I reverse time, okay? So what I will see that this thing is moving away from the wall. Yes.
These two contradict each other because there's no inherent reason for it to
So, right, okay, I mean, the thing is that I should reverse this force as well. I'm reversing time, I'm reversing this force as well, and then this is going away from the wall. But now the argument is that in this situation, if someone is sitting here and observing it, this really looks like this thing. There is a reflection symmetry across this plane. This thing is reflection invariant. And on this frame, it looks like this object is moving towards this guy, just like this falling, but it's now moving away from the wall. So we have now contradicted what we started with. Did everyone follow this argument? So this cannot happen, and the only resolution is rightly pointed out that they should fall straight. So there is the same set of arguments for this problem as well. So what will happen in this problem? Which direction will it rotate? Will not rotate, right? Okay. So the same argument, right? So what you can do, you can assume that it is going to rotate in one direction, okay? Then what you do is that you reverse time and say, okay, then if I reverse time, the force is acting in this direction, simply means it's going to rotate in the opposite way. But again, you can see that there is a reflection symmetry in the problem. So if I reflect this problem about this axis, I get a situation where this thing is coming towards me, but it's now rotating in the opposite direction. Is this okay, everyone? So there is a contradiction no matter which direction I choose it to rotate, and that only resolution is that it shouldn't rotate. Okay. So,
hello, sir.
Yes.
So will you please repeat what you mean by the reflection symmetry? I think I didn't get it.
Okay. So let's take this problem, and suppose you have a force acting and it's moving down. Okay. Now this direction, let's call this Z, this is infinite really, okay? So it doesn't matter. So if I reflect the whole problem about some axis X of this form, the problem is identical. So if I just change now, if I change the direction of the force, this problem should be identical. There shouldn't be any difference, right? So there is a symmetry around this plane where you can reflect things, and we should have the same results no matter what. So the question then, now the argument is that, okay, suppose when you are looking at this problem, you assume the particle to be moving towards the wall. Now if you reverse time, so if you reverse forces, okay, the particle should move away from the wall, but this is okay, this is reversing time. But now these two problems, going this direction and these directions, are identical problems. They're not different problems, because someone from seeing here will exactly look like the problem that we solved first. So in the second version of the problem, it seems like that the particle is moving in this direction but moving away from the wall. In the first version, you assume that it's moving towards the wall. So that's why there is a contradiction between these two. Is this okay?
Okay. Yeah.
Okay, so I think with that, we'll see that we'll use this once more when we start talking about swimming today. So let's now move on to actually start thinking about swimming of particles. So let me start with the following question, which is general, which is not necessarily true for Stokes' law. It's true for anything. What does it really mean to swim? So you can think about our examples when we go to the pool. What does it really mean to swim?
Self-generated.
Okay, it's self-generated flows. That's correct. Anything else? Okay, suppose I will give you another example. Suppose I'm in a fluid, okay, and there is a rope. Someone is pulling the rope and I'm hanging on to the rope. Is that swimming? No, right? So you're being towed in that case. So that's not swimming. So swimming, like he pointed out, that it's self-generated flows. But in other words, what you're doing is that you're going to deform your body in some way. And by this deformation, you generate some propulsive forces from the fluid which you're immersed in. Okay? So you push the fluid, get some propulsion, and then you move forward. But remember, there is no external force acting on you. So what is resisting your motion when you move forward?
Viscosity.
Viscosity. So there is drag, right? So drag is resisting our motion, but this is sort of a subtle point because you see that when you're moving, you're generating the force or you're generating the propulsive thrust from the fluid by deforming our body. But as you move, the fluid itself is also resisting your motion. Okay. So for any general sort of swimming in any Reynolds number, you can always write this. M swimmer times du dt. So this is my propulsive force. This is my drag force. Both of them are coming from the fluid, and then I'm moving in the fluid. Okay, and this is happening at every instant of time. Now suppose I'm swimming and my velocity is not changing with time, which means I'm moving with a constant velocity. Okay, so what does that mean in this problem? This should be 0, right? So then what it means is that when I'm swimming without acceleration, the net force acting on me is 0. So the propulsive forces and the drag forces from the fluid exactly balance. While this could be a special case for me, only when I swim with constant velocity in a swimming pool, but this is always true for the bacteria or the microorganism that we're thinking of, because these terms, like we just mentioned, these terms are subdominant. Okay, so these terms are not there. So at every instant of time, as this microorganism moves on, I have this relationship. So at any instant of time, it's moving. So I will just draw this. So this is the microorganism, say. It's going to deform its body. However, at any instant of time, the net force acting on it is 0, because there is no external force, no one is pulling it. It is moving purely by pushing off the fluid, and the propulsion and the drag should balance. Okay. There is another property of swimming, which sort of I drew over here, is a property that as you swim, you need to cyclically deform. So you need to keep moving. You don't want to move once and then stop. You want to keep swimming. And moving on or swimming on simply means that you're cyclically deforming your body. And this is again true for us. If when you go in a pool, when you're performing, say, the freestyle, whatever swimming stroke, you're periodically doing it. You're not doing it once and then stopping. So this is a periodic deformation or periodic cycle through which you always go, and then you move forward. Okay. The only difference, and the key difference here, is that the net force on the swimming object is always 0. And now just to point out that these are distributed objects, right? I wrote this as a decomposition of propulsive forces and drag forces. But alternatively, I could have said that there is some force vector, let's call that T. This vector tells me what is the force per unit area exerted by the fluid on me, right? So this statement is equivalent to saying that integral of this force vector on my whole body surface is 0. And this is 0 at every instant of time. Yes.
So when you said this statement is always true, let's say if the microorganism is at rest, it will need some acceleration to go to a velocity, then it will be constant.
So, okay, so that's absolutely correct. So if you start from rest, there has to be some acceleration. What we estimated last time is that whenever you have acceleration, you have a term that looks like this, ms du dt. It turns out, even when you have this term is very subdominant compared to the dominant forces. So you have acceleration maybe for a small time instant, but it turns out that this term is extremely small compared to the other terms in the problem. So it's a dominant balance. I agree completely with you. It's not like this term is not there, vanishes, but it's much smaller compared to the forces that's showing up in this problem over here. So is this statement clear to everyone, that at any instant of time, doesn't matter which instant, the net force, the force, integrated force from the fluid on the object is 0. Okay. So that's the other property of swimming. So now let's let's get to the first example, and this is effectively almost a theorem. It's an example of what cannot swim in Stokes law. Okay. Suppose I have an organism that looks like this. Okay, this color is not great. So there is some angle theta. So these are two rigid links that are attached with a hinge. Okay. So it's a one hinge object, and all it can do is just this. Okay. That's all it is allowed to do. So suppose this is time t equal to 0. Next time it becomes like this. Next time it becomes like this. And now you come back. So this is T1, this is T2, T4. Oh, sorry. 3 and 4. Okay. And this is T0, sir. Let me just draw a line here. Let's see what I mean. Okay. So that's all it does. Okay. So this is a periodic set of motion, because at the end, at time t4, you have come back to its original position t0. So you open and you close. You open and you close. So what happens when you're closing? So if there is an object that's open like this and it closes, what happens to the fluid inside it? It goes out. So it squirts out fluid in this direction. And when it is opening, it sucks fluid in. Okay. So now, can this object swim in Stokes law? That's the question. What do you think? Possible or not possible?
Not possible because of the reversibility.
Okay, so there is an answer that it's not possible because of reversibility. Is this possible in high Reynolds number? It's like if you, what is sort of your intuition if you have an object that's moving in sort of, say, not in Stokes regime? That's possible. Okay, so there was an answer that it's not possible because of reversibility. So what if I tell you that you go through this sequence of shapes quickly and you close much slower? Suppose this time takes you, say, t, and this t left, and this t right. And now I say that these times are different. Will that change the scenario? It will? So let's take a vote. Let's take a vote. Who thinks that will change the scenario?
What kind of analysis?
So it's still Stokes law. Still Stokes law, zero Reynolds problem. Who thinks that it will change the scenario? It moves. So one for moving, 2 for moving, 3, 4, 5. Okay, and not moving? It's almost equal. Some people are not participating, but that's okay. So it's almost equal. So what's the intuition that why it should move? No? So the point is that, okay, I am opening faster and then closing slower. And the intuition is that, okay, maybe the fluid flows look different in those cases. And that's why this will move. So this is exactly our intuition that we have in the world we live in. This is exactly what's going to happen if you perform this experiment in water with something that's flapping very fast. But it's not the world of where we live in, because whenever you're saying that something opens fast, something opens slow, you're saying something about time, right? But is the time in the governing equation anywhere? There is no time, right? So there is no sense of whether I'm going slow or whether I'm going fast. It's only the geometry that matters. So if you retrace, so what is happening essentially, now if you look carefully, going back to the point of reversibility, in these two halves, once you have finished it, you're essentially going to, if you reverse time now, you're going to retrace the shapes back, okay? So this stroke or this motion is time reversible, or it's a reciprocal motion, and that's the only motion that you can have with one hinge. And it doesn't matter whether you move fast or slow, because there is no time in the governing equations. As long as you're going through this same sequence of shapes, you're going to end up in the same position at the end of one period. Okay, so maybe a little bit abstract, but this helps is that this is some sort of shape space. So there is really one coordinate in the shape space. In this case, that's theta. And all you're going to do is that you're going to move in this direction and then you're going to move back. That's all you're allowed to do, because remember there is this constraint that you need to deform cyclically. Okay, if you of course open up and then stay there, then you have moved some distance, but that's it, that's your life. You have opened once in your life and then you have moved that much and then you will remain there forever. But if you want to keep moving, you need to keep deforming, and now you're moving on this 1D line back and forth. Okay, so you're not going to move anywhere. There's another way to see this. Let me show that. Is that I can write down the fluid velocity. This is again sort of a scaling kind of argument. I can write down the fluid velocity u as something that's proportional to theta dot times function of theta. So what is theta? It's this. Theta dot is the velocity by which I'm opening. So I'm driving the fluid through this velocity in the boundary. So you can imagine that my solution to the Stokes equation is something proportional to theta dot times f of theta. So f of theta is some geometric function of theta, which can be there. There's no problem with this. But this is a total derivative. Right? So now if I compute what is the average fluid velocity, if I integrate over one period, one complete period, that means you go from this shape and you come back to this shape, right? So we integrate between this. Simply get f of t minus f of 0, and that's 0. Right? So what I did is that, since this is a total derivative, I just integrated this over the whole time period. And all it matters is what is your shape here and what is your shape at the beginning, and these two are identical, so you don't move. There is no displacement of the fluid, but there is no displacement of you. So this thing, the fact that this cannot move, it's called the scallop theorem. So I will just write it. Scallop, as you can imagine, scallop has this one hinge, so that's where the name comes from. It's called the scallop theorem.
So if the hinge at T0 and T4 are given slightly different,
then this will work. Yes, so if there are more than one hinge, okay, if there are more than one hinge, and if things are slightly different in different instances, then it will start working, and that's essentially the next step, where one way to break this theorem is to have more than one hinge. That will just do the trick. Okay, so this was pointed out by E.M. Purcell, who was a physicist. He used to work on NMR, but then he worked also on these sort of problems, and he had this theorem called scallop theorem, and in the paper that I sent out to you guys, you will see that there is a large discussion about this scallop theorem. So in summary, a one-hinge swimmer can never move in a Stokes flow. Okay.
How big are scallops?
How big are scallops? I think they are centimeters, something, right?
Can be about this big.
This big, centimeters. So.
And if you just search a video of scallops, I mean, it literally sounds very good. It just, fly around and water. It's very good.
Okay. So let me do one thing. So this is a scallop theorem. Before we talk about how sort of you break this and how you swim now, let me just okay, maybe I will show the video later. I'll just go over one thing because I want to do something else. I want to show a video. So okay, now we have figured out what doesn't result in swimming. The question is, what will allow you to swim? And one suggestion that was immediately pointed out, that what if you have more than one hinge? Then of course you can sort of break, or you can try to break this time reversal symmetry. You can design strokes even with two hinges that are time reversible, but you can also design something that's not time reversible, which means if you run the movie backward, you will see different shapes, and then you can move forward. Okay. So we'll come to that example in a second, but let me give you a simpler version. Suppose there is an object, and now you have filament like this. So let's draw it with color. I have a filament, which say I have a filament like this. So now I say the word filament because I'm not going to make it rigid. You remember this problem, both of these links were rigid. Here now I'm making this a floppy object, okay? It's a flexible object. And it does the same thing. All it does, it wants to go up and down. But now since it's a floppy object, since it's a deformable object, what will happen is that as it is going up, as it is moving up, you can imagine the fluid is sort of pushing down. So it will deform like this. Okay? But now, as you are going to come down in the other direction, you're going to deform like this, the other way around. And so if you do that, okay, even though this looks like almost this problem because you have just one hinge doing this and this, but since now you're allowing it to deform, you're breaking the time reversal symmetry, because now if I look at the sequence of shapes that you trace out over time, the sequence over the whole period is not time reversible. If I just play the movie backward, I won't get the same set of shapes, because in two directions you're getting two set of shapes as opposed to this one. Okay, so this is one way to break time reversal symmetry, and I have a movie I will show you that people have done this in experiments where just designed a filament with a paramagnetic beads, and they turn on a magnetic field. All that the filament does is that they do it, and this starts swimming immediately. So this is one way to break time reversal. So the main principle is break time reversal symmetry. Okay. So this is one way. What's the other way? So let's take another example. And this example is something, I mean, this is more biologically motivated. Suppose you have something of this sort, okay? So this is like a sperm cell. It has a head and it has a tail. What it does is that it propagates waves along this tail, right? This is sort of the textbook picture, that there is a cell propagating waves and moving through the fluid. But why does propagation of wave allow it to swim? Like, what's sort of the basic argument? If I say you that, say this is X, say this is Y, if I tell you that it's something like suppose I tell you this. So there is a traveling wave that's propagating. Does this break time reversal symmetry? Does this break it? Is there a way to see that? If I put, yeah, sorry, anyone, you go ahead.
If we reverse the time t to minus
T, don't get back. Yes. So this again breaks time reversal symmetry. So this can swim, this can move. Okay, that's another way to do it. There are bacteria, and so we're going to discuss this case in extent today. And I will just tell you that okay, E. coli, it is a bit like this. So this is a filament, this is a floppy object. It's like a flag that's waving. This is a rigid object. This is like a corkscrew, okay? This is a helix, but now you spin the helix, some angular velocity. Does this break time reversal symmetry? Is there a consensus? Will it break? So this broke time reversal symmetry. The question is now, I have a rigid object. This was a floppy object, right? This was waving, this is like a flag, which is waving, right, dancing. Here I have a rigid object. It's a helix, and now you're just spinning it, rotating it. And the question is, does that motion break time reversal symmetry? The whole body will rotate. I mean, it turns out the head will rotate in the other direction, but okay, that's a second question. But do you think this breaks time reversal symmetry? Okay, if you think of this problem. If you take a corkscrew, okay, put it in a cork and rotate it, does it translate? Does it move some direction? So it has some sense of which direction it's going to. So that's exactly what you need to build in to break time reversal symmetry. You see, this problem didn't have any sense of which direction it's going to. Because it's the same argument. You could have said that I assume that this guy is moving in the right, and then you could have reversed time, and you would say that same shapes are going, so you would have ran into a contradiction. But as you rotate this, since these are chiral objects, this has some handedness to it. The moment you start rotating, there is a preferred direction. Okay, so this also breaks time reversal symmetry. And another way to think about this or show this is that I will show you a movie. If you just rotate a helix and look at the pattern that it generates on two planes, you will see that those are essentially waves going on. So this is also breaking time reversal symmetry, and this can also swim. And this is how bacteria like E. coli swim, and this is how many eukaryotic cells like sperms with flagella swim by propagating waves. Okay.
How is the first case time reversal breaking time reversal?
So the first rate is breaking time reversal. So if this was a rigid object, then all it will do is that it will go like this, right? It will do this. And that doesn't break time reversal symmetry. But now this is a floppy filament. So as you move up, as I'm moving up, I'm sort of experiencing forces from the fluid, and that deforms me. So I bend in one direction. And when I'm coming down, I bend in the opposite direction because the fluid is now sort of pushing me from below. I bend in the opposite direction. And as a result, the shapes that you trace in two halves of the problem, they're not identical. They're different shapes.
So this would be in two halves of one, for like say once.
That's right. So essentially, you can ask this question that whether y of x at time, so if t is your time period, if t minus t is same as y x at time t. So this is, look at this problem. So this is my time period t. If I just move from t minus t, this shape is same as this one. On the other hand, here this won't be the case. There will be one shape which will be upward and one shape will be backward.
This is for one time period that.
This for one time period, you will still move, yes.
So if we look at the same case, but for like the next time it has moved up, how would it be not? How would it still be breaking time reversal? Because
So after one time period, you come back to say this is your time t0. After one time period, you have again come back to this. So if you move in one time period, you will keep on moving, right? It's a cyclic deformation. So all you need to prove is that it moves in one time period.
Is t minus t a good thing because TL and TR can be there?
Sorry?
Is t minus t a good thing because in that case TL and TR might be different?
Well, I mean, in TL and TL are different, but then the issue is that in this case, to close, it will take longer time. So this could be different, absolutely. So maybe this is not the right thing to measure, but as long as you repeat the shapes, you will get back. You will just, the closing time will be different. Yes.
In that time, like total time.
So that's, I agree. If there is difference in time, then you should not compare TL to TR, you should compare something else. I mean, you should compare something else over here.
I'm asking, like, should we consider TL plus TR as the one time period?
Yes, TL plus TR is your whole time period.
Yeah,
Yes.
TL plus TR is the capital T, right?
So here time period is what? Here time period is, in this problem is 2 pi over omega. That's your time period. So if you do this calculation, so if you do plug in t, then you'll find that there is a plus omega t showing up as opposed to minus omega t. So there's a sign shift, so things are different. And it's the same reason, because the moment a wave starts propagating, there is a sense of direction, which direction it is propagating, right?
Yeah.
Okay.
And here's the first one.
Yes.
So is it like there is a force that drives.
Right, okay, that's true. That's true. So inside there has to be some mechanism to drive it. So in the experiments that I'm going to show you, that's not actually true swimming, because what they do is that they drive it by an external field. So that's not really true swimming. But here, if this is not a biological example, but if this was a biological example, there has to be some internal mechanism to do this.
Yeah. So ideally, what we are looking at the flagella or whatever it is. So there, the force is acting at the tip, right? Like the tip is trying to drag the old lump.
No, the flow forces are acting everywhere. So you mean actuation is happening here? Is that what you're saying? Oh, I am confused with the question.
So like,
Let's do this problem. So you're saying that there is this shape.
is it like the tip of the tail is being dragged up?
No, it's not the tip of the tails being dragged up. So in the experiments, what happens is that these are made out of some paramagnetic beads, and then you apply a magnetic field. So there is a force on all the beads, and that's the force that you're oscillating with. So there is a time frequency for the oscillation of the magnetic field. So there is a force on every point of the filament that's trying to push it up.
So then why does this one move farther?
That's purely because, I will come to that, there is because of two reasons. The drag in Stokes process and isotropic, I will really come to that in a moment. And then this thing is floppy. There is a fixed end, there is a boundary condition in the problem, and this is a floppy object, so this is an elastic object for which you need to solve the equation. Yeah. Other questions? Yes. Yes.
We indicated f of theta over 1 time here.
Right.
So the shape is not different. If you take half a period, does it mean during
Half period can move. Yes, absolutely. Absolutely. Right, correct. That's correct. So that's absolutely true. You can move half a period, and if that's all you do, that's what I was saying. That's all you do in your life, then you will swim, but you will swim only once.
You will come back in the next half.
Yeah, once you do this, you will come back. There is no other way.
Also, talk about breaking the symmetry.
Yes.
If you are able to tell, if you are shown an arbitrary state, and if you are able to tell if is it coming back, or is it is it going from the initial state, or is it coming back? If you are able to tell, that means there is no symmetry.
Can you repeat that? So if I'm able to tell from the stroke.
If you show me the shape at T3, I don't know whether it's actually T3 or T1.
Exactly, that's correct. That's correct. If you are able to tell, then it breaks time reversal symmetry. That's exactly correct. Perfect. Yeah, that's correct.
We've been looking only for one-dimensional experiments,
right? Right.
In the first, if the picture I'm trying to draw.
I mean, this is still in a 3D fluid bath, but it's moving in one direction.
The net motion along one dimension is not non-zero.
Non-zero. The other direction, it doesn't move. It can, that's correct, it can. It will average out, absolutely, absolutely. So actually it turns out that this guy, E. coli, actually has a helical trajectory. As it swims, it doesn't swim in straight line, it swims like this. And the reason it happens is that there is a mismatch between the alignment of the cell body and the alignment of this rotating object. If they're perfectly aligned, then you are exactly correct. Things will average out and you will keep swimming straight. But if there's a misalignment, you can get a torque which sort of spins you as you move along. Okay, so let's look at some movies. There is iPad. Okay.
So for the first case,
yes.
Shouldn't all the beams or like the complete filament should move above the pink line, right?
Above the pink line. No. So depends. So that depends on what is the boundary condition that you've implemented on the head. So if the filament is really clamped, which means that the angle of the filament is not allowed to change, then it will move up. But if it is hinged, if it is allowed to rotate around that end, then this would be the shape. So let me. Okay, so this is not a swimming example, but this is a consequence of this theorem, and there are subtleties in this experiment because the Reynolds number is not really zero, but you still see some manifestation of the scallop theorem that I was talking about. This is a very nice problem. This is a fish, okay? This is a larval fish. I have written down the scientific name, I can tell you. It's called Sparus aurata. I won't remember it after this. It's roughly 4 to 5 centimeter. And they have an extremely high mortality rate after they hatch. So 99% of the fish, they die after they're hatching. Okay. The reason they die is that they get starved. They cannot get enough food to survive. And the food that they typically eat are these zooplanktons that you're seeing around. Okay. Okay, so that's the setup. And you will see what's happening. This is a tiny fish. All it does is that it opens its mouth. So the food comes in and then it closes its mouth back. That's all it does. Okay. And we'll see what happens. So it keeps doing it, but just can't get the food, right? So this is horrible, absolutely. And so these guys die, and what you see in the plot over here is these are days after hatching. So this is their age, and this is their feeding rate. Okay, so when you are young, when you are small, you're effectively in this sort of low Reynolds number regime, and you cannot feed. You die. But you get some food, but if you are robust enough to survive that age, then you become larger. And remember, Reynolds number is rho u L over mu. So if your length is large, so if you just survive and become a larger fish, then you go to higher Reynolds number. And just like Aditya mentioned, a scallop can swim by doing this. It can also get food by doing this. There's no problem, because if you look carefully, you'll find that it's opening its mouth and closing it at 2 different rates. So look carefully once more. This. So it does this, but it just doesn't work. Okay? So their survival chance actually increase dramatically once they get older, but younger fish, it's a trouble. Okay? So since, I thought I will show you this example later, but since there was this number of these questions, so let me play this movie. So this is this artificial swimmer that I was talking about. These are designed by sort of linking paramagnetic micron-sized bead by DNA. Yes. So, okay, what we're looking at, the case when their dye is not 0 Reynolds, but this is roughly Reynolds 20 to 30. So that's not definitely 0 Reynolds. So, yeah, you should take this with a pinch of salt. But
Fish were to survive in a high viscous medium,
then it's doomed, really. Yes. But I think last day someone was asking this question, is that if you're really designed to survive only in high viscous environment, then there should have been an evolutionary pressure to feed somewhere else in some other way. I mean, if evolution wouldn't have said that you're just allowed to do this and you have to live in a very viscous environment, that would have been horrible. Yeah. Okay, so this is this artificial swimmer. Can I get the lights off, please? Yeah, okay. So these have these paramagnetic beads. Okay, and then these guys, you'll see that they have this is not really swimming because this is still driven or actuated externally, and you will see, but this thing sort of beats and then this object keeps moving. Okay, so that's the mechanism here. Okay, I'll come back to all the other examples later on, but this is also the rotating helix problem. So this is another good illustration of how just rotating the helix would break time reversal symmetry, because you already got the piece that propagating waves break time reversal symmetry. Here, if you look at these two planes, okay, YZ and ZY, as you rotate the helix, you see that they're essentially waves traveling, so you also break time reversal symmetry. Okay, so what I will do for the rest of the class is I will try to talk about this case, which is the waving of flagella. Okay. The reason I want to talk about this is sort of a general mechanism to move or swim in low Reynolds number. This also applies to the rotation of the corkscrew, and this of course applies to things like sperm. And the real mechanism, I will give you the punchline, the real mechanism is called drag anisotropy. And I will explain what it means. Okay. So just remember, the problem that we are planning to study looks as this. There is a cell that's propagating these waves along its floppy flagella, and we want to figure out what is the swimming speed, or we want to understand why this works. Of course, you have established the fact that this breaks time reversal symmetry, but we will try to get a more fundamental reason of why it swims, because as you will see that there could be instances, or you can, in principle, design fluids, even where you break time reversal symmetry, this won't lead to locomotion. Those fluids don't exist, but you can, in principle, design something like this. So that's this problem that we want to study. And what I will do is that this is a very hard problem. By hard, I mean you have the head, you have the tail. It's fairly complicated. What we'll do is that we'll assume the head is not there, and we'll make the assumption that this flagella is infinite. Okay. So we'll do the problem for an infinite line of waves. That's this setup. You have a set of traveling waves that are just propagating. If you look at, okay, the equation is not there. If it's propagating with some velocity, v. And there are two things that I would like you to remember or point out, because it's hard to sort of switch between the board and this thing. So I'll just like you to remember, which is that as these waves propagate, if I just look at material points on the filament, what do I mean by material points? Is that if I take two markers on the filament and see how they are moving, remember they are not actually moving with the wave, they are just going up and down. Okay? That's property of waves. You just go up and down, and then you transfer information. Right? So that's one thing that I would like you to remember. And this is really the same wave plotted with very few elements. This is over one wavelength plotted with very few lines. And that's intentionally done in this way, and we'll see in a moment why is that the case. So just look at this thing. Okay, I should just loop it, otherwise it's okay. So this thing, as you can see, that this segments, as this segment is going up, the other segment is going down. So if you think of this as some sawtooth, one segment going down or up means the other segment coming down. Okay, that's the only thing that I want you to remember from this. Okay? And we'll see how this is crucial for propulsion in low Reynolds numbers. So let me stop share, and I will use the board now. Okay. To do this problem, and to tell you something about what is called and this is also implicitly discussed in the video lecture, but I will discuss here, is that suppose I take a rod, and this length is L, its radius is A, and as you can imagine, A over L is 1, is epsilon, some small parameter. So this is a long, skinny object. In this case, it's just a rigid rod that's there in the fluid. And now I ask you the following question, that suppose I move it with a velocity u. So when I'm moving it with a velocity u, of course, I'm applying a force, that's why it's moving. Okay, so I'm dragging it, I'm towing it with some force, that's why it's moving. Now I ask the question, what will be the force? So if this is the force, what do you think would be the force if the length of the rod was, oh, it's horrible. Let me just draw a line. Okay, what would be the force if the length of the rod was 2L? What's your guess? I'm moving with the same velocity u. What's your guess? Same or more or less? Okay. It will increase the I will need more force, right? It's longer, right? Okay, so let's do this. Just recall the sphere sedimentation problem. What's the drag on the sphere? right? So we increase the radius of the sphere by 2, what will happen to the drag? It will increase by a factor of 2. So if I want to pull it with the same velocity, I will need to double my forces. Is this okay? So intuitively, this is also what should happen here. And of course, there is another dimension in the problem, which is the thin dimension of the radius. But that's so small that should not come really in the picture of calculations. That's our assumption. So is this clear? That I need roughly 2f to do this thing. And of course, if I make it 3l, I need roughly 3l, roughly. So as you can see, for long and skinny objects like this rod, it's probably better to talk about force per unit length instead of talking about the net force. Because if I know the force per unit length, I just multiply by the length, then I get the total force. Correct? Is everyone okay with this idea? So what I will do is that I will say that any point on the center line is described by this coordinate s. It's called arc length, but it's essentially running along the center line. Tells you how much you have traveled along the center line. And I can say that force, so I will denote this with lowercase, force per unit length, remember this is not total force, this is force per unit length, is by Stokes' law is proportional to the velocity with which you are moving. Correct? Agreed? This is something that we have established. Yes?
So the drag is like ideally like how the surface is being resisted to the
Right.
So when you are moving on this direction, it's ideally the tip that is.
Yes, but the still fluid is still flowing past the object, right? So there is still friction along throughout the backbone. Yes. So, but you are going the right direction. Your intuition, what Naveen is saying is that if I take this object and pull it this way, naively I would imagine that the force I require to pull it should be smaller as opposed to if I pull it this way, right? So we will see whether that's indeed the case. Okay. What should I put here to make it equal? What should I put it? Put there some matrix R. Now can anyone tell me what should be the dimension of the matrix R?
Something marked by area, because that's force by area.
This is force per,
Volume.
this is force per length. Okay, this is force per length. So this is force per length, this is velocity. So you can imagine that this is going to go as viscosity. Because viscosity times velocity gives me force per unit length. And it sort of makes sense that if I increase the viscosity of the fluid, I will need to pull it by more forces. So this should be proportional to viscosity. Okay, so computing R is actually a challenging task. Okay, I am not going to compute what R is. You have to solve the Stokes equation, do some approximations, and get to R, but I will just give you the result what R is and tell you about its implication. So R in this problem is given by where C parallel is typically half of C perp. I will explain what I mean by these things. And C perp is roughly so let me explain what this is, because there's a lot of terms here. So first, T hat that I've written over there, this T hat quantity is an unit vector, okay? This is the tangent vector or unit vector that's telling me which direction this rod is pointing at. So if the rod was this would be T hat. Is this okay? So T hat is clear, right? what I've done over here is that I have taken what you can call an outer product, or a dyadic. So T hat is a matrix essentially. Okay. So on other words, I don't know whether you're familiar with this, but we can say that if R is a matrix, I can say that the ij component of the matrix is T hat I, T hat j. This is not R, so let's just use some other thing.
Hello,
So,
sir.
yeah.
So we cannot see the blackboard actually. It would be better if you zoom out.
Okay. So not me.
No, I think we have adjusted now.
Okay, we adjusted. Okay. So this matrix R. Okay, what I was saying. C parallel and C perp are called drag coefficients. So kind of makes sense. Both of them are proportional to the viscosity of the fluid, and if you multiply by them, you get the force per unit length. Okay. So let's write this matrix for a specific case, and you will see what it means. By the way, if T
C parallel is approximately equal to half of C parallel.
no, this is I didn't write it. So this is a result that comes out of the calculation. So you have to sort of take my word for it. There is no way to prove it. I mean there is a way to prove it, but no, this is beyond the scope of this class. Okay, so this just comes out of it. Okay, can anyone tell me what this matrix is, or what this sort of thing is? I minus tt. So t is a unit vector, remember. What does I minus tt mean? Have you guys seen projection operators? So what if I take this I minus t hat and multiply this or dot it with a vector that's pointing along the direction t? What will be the result? It will be 0. Does everyone see this? T hat is an unit vector. Okay. So identity dotted with t hat gives me t hat. So this is just alpha t hat minus t hat times t hat dotted with t hat. That's the dot product mean. This is 1. So this is 0, right? So what this does is that it removes any component. You multiply it with any vector, and you write the vector as components along t and perpendicular t. This matrix or this operator removes any component that's there is along t. That's what this means. Is this okay? So let me just write down for a particular case how this matrix look like. Okay, so that will be easier. So suppose this is your rod. This is angle theta. See, so this is t hat. This is x. This is y. Okay. So what is t hat in terms of x and y? Okay, it is cosine theta x hat plus. Okay. So remember this matrix, if I call this Dij, this matrix D is t hat and Dij is t hat I, t hat j. The same thing, okay? So these are the same things. How will I construct this matrix? Yes, so it is Dij, just if I put I equal to 1, j equal to 1. So like dxx, that is tx, so that should be cosine square theta, right? What about the xy component? Okay. And you will get the same thing here. And you will get what? And of course, this part is just identity minus that. Okay, that's what this is encoding. Okay. Okay, remember this. That's what t hat means. I mean, that's what t hat means. This what this is matrix. This means. Okay, so we have this result, and let's do 2 experiments and try to verify whether Naveen was correct. Okay. So I take this rod and I move it with a velocity u along the direction t. So say let's just draw the arrow this way. So this is u. So my velocity vector u is some u naught times t hat. Now without doing any calculation, if I multiply this vector with this matrix R, will this term contribute? No? Yes or no? No, okay, so this won't contribute, so this term will, right? So let's compute that then. Force will be what? It will be C parallel u naught times t hat dotted with t hat. And that is what? Anyone tell me? No, just say it in terms of C parallel. C parallel u naught. What is this operation? Is it 1? It's a t hat. Okay. So that's t hat. Okay, that's F. So this is the force I need to pull the object through the fluid with a velocity u naught. Is this clear to everyone? So now I do the same experiment. I move the rod with the same velocity, but instead of moving it in this direction, I move it in this direction. So I'm going to draw the rod perpendicular to its long axis. So can anyone tell me, so if I can write, the case 2 would be the following. This is case 1. This is parallel, really. And case 2, which is really the perpendicular case. If I'm moving, if the velocity vector, if u is now u naught times, so it's in this direction. So if it's easier, think of this as x, think of this as y. Okay. Now can anyone tell me whether this term will contribute? Will it? It won't. Fine. Will this term contribute now? It will, right? What will be the value? So let's make our life simpler. So let's take this as x, this as y. So u is essentially u naught times y hat, effectively. And this is I minus x hat, which is y hat, right? So this will just give me f of s is c perp u naught t hat perp. Is this okay? Is it okay with everyone? So now I have a relationship that C perp is twice the value of C parallel. So is this force same as this, larger than this? What is it? Larger than this. So indeed, this intuition is correct, right? That if I'm pulling it along the long axis, the force that I need to pull it with is different if I pull the whole thing on the transverse axis with the same velocity. And it's roughly twice. Not exactly, but roughly twice. So you can call this, what this phenomena is known as, it's called drag anisotropy. And name is sort of evident what it means, that drag for a sphere was isotropic, it was same in all directions, there was no preferred direction. Here the drag forces depend on which direction you're moving with respect to the object. Yes?
Is this the total drag with pressure and this?
It's with everything. It's with everything. So this is this relationship which I have removed now, that F is R times U, that comes from solving the full Stokes equations. So it has everything in it.
This R is only for extremely thin objects.
Sorry?
This R is only for extremely thin objects.
It's only for extremely thin object, correct. That's correct. So it's only for when epsilon, this radius over length, is very, very small. But just for the numbers, since you asked this question, if I think about an E. coli flagella, which is rotating like a corkscrew, the diameter is roughly 20 nanometers. Okay? And the length is some tens of microns. So if I compute A over L, right, that's roughly in the order of 1,000. I mean 10 to the minus 3, sorry, epsilon is 10 to the power minus 3, 1 over epsilon is 1,000, roughly. Yes?
Is it only for linear or if it's like...
Okay, so we're going to come to that. That's a very good question. So the question is, I wrote this for a rigid rod. Does this relationship hold if my object is something of this sort? So the answer is yes. So you can think of it, the way to think about it, yes, exactly. The way to think about it is that you can sort of chunk it in small pieces. And these are all sort of segments of rods that make up your filament. And since this is force per unit length that I'm thinking of, this relationship still applies. And of course, to compute the net force, you will have to integrate along this curve, but that's something that you have to do. So let's just remember this relationship, that forces or drag forces in Stokes laws are anisotropic. Okay, let's just remember this. And with this relationship, let's show how traveling wave things or rotating corkscrew can generate thrust and move stuff in fluid. So what we'll do is that we'll do this problem now. So let's erase this piece. Okay, suppose I have this rod and this thing is moving. So this is x, this is y, this is theta, and this object is moving upwards with some velocity u. Okay, so I've prescribed the velocity u with which this object moves. So I want to compute the other problem now. So I know the velocity u. I want to compute what is the force exerted by the fluid on this object. Okay, so I will, you again will do this, and I will put a minus sign and we'll see in a moment why. Okay, so the reason I put a minus sign here, because I'm thinking about the forces exerted by the fluid on the object. Okay, so this is a drag force. The reason I didn't use a minus sign here, because I was thinking about what is the force I am applying to pull the object. They're essentially the same, because remember, force, the drag force plus external force is always equal to 0. So they just have different signs. Okay, so the fluid is applying a drag force of F, I need to pull it with a minus F force. So they're the same thing, but I just added a negative sign to show that if this guy is moving in the upward direction, this is the force. So I won't do this calculation. I mean, I've written you the matrix T hat, T hat. So you know this, you know both of this matrix. You know this matrix, you know this matrix, and you know what U is. So you can just do the whole calculation. It's essentially all multiplication, but I will just tell you what the result that comes out of it. And I will tell you about this result because it's interesting. So force is a vector. It will have components in both x and y direction, but I will just tell you about this stuff. So this is sort of a interesting or strange result. it tells you that as I take a rod and move it upwards, perfectly vertically upwards, the fluid applies a force in the horizontal direction, the x direction. Okay, this is very counterintuitive. This is not what we will see for a sphere. So if you take a sphere, pull it vertically upward, the fluid only will apply a drag force in the opposite direction. But here, since this matrix has this anisotropy built in it, there is a force that you get in the x direction by pulling an object only in the y direction. So this is a drag force. Okay, this is a force exerted by the fluid on the object. And remember, C perp, I've written there, C perp is roughly 2C parallel. So this is a positive quantity. C perp, this is a positive number. And what sits over here could be positive or negative depending on what is the value of theta. Okay. But right now, the way I have drawn, this is the whole thing is positive. So as you move this, you get a push in this direction. Is this clear? So now let's get back to the flagella case. Okay, so let's solve this case now. So now remember, the way I'm modeling the flagella is that there is a wave that's propagating in this direction. And by this sort of sawtooth approximation that I did, it looked like this, right? I mean, you can do it a couple of ways, but let's do it this way. So there is, you can think of this as a rod. Think of this segment as a rod. As the wave propagates, this guy is coming down, this guy is going up, roughly. Is this okay? Where? This one? Well, I think it's C perp minus C parallel. Did I make a mistake? Well, we can do the calculation. Sorry? So, okay, so there is only difference. There is a minus sign sitting in front of it. Okay? So this is the, okay, this, just to repeat, this is the force that the fluid is exerting on me. Okay? And virtue of third law, I'm exerting the equal and opposite force on the fluid. So it depends what you are calculating. So I'm computing what is the force the fluid is exerting on this piece. Okay, so there are these two segments of rod. One is moving in this direction. I mean, this is just really oversimplifying things, but you can think of that there are these two pieces of rods. One is moving in this direction, the other one is moving up. Okay. So now tell me, if I have this piece that's moving vertically downwards, which direction will the fluid push it? Which direction? Let's do this. So this direction is going. So where should the fluid push it? Left, right? So this gets a push in the left direction. Which direction will this guy get pushed? Just moving up. Which direction? Let's just use this formula and just stare at it. Okay. So both of them are getting pushed from the fluid in the left direction. And you can do this, keep doing this for all segments, right? So all the segments, by just moving, like I showed, the material points are just moving up and down, but as these segments move up and down, they're getting a thrust from the fluid, or push from the fluid to move towards the left direction, okay? And the thrust is of course proportional to how much anisotropy you have in the fluid. So if C perp and C parallel were equal numbers, then you wouldn't have got any thrust. You're only getting the thrust because the drag forces are not isotropic in all directions. Okay? And if the wave is propagating in this direction, like in this case, if I add up all these thrust forces, I have a net thrust of this whole thing in this direction. And typically, of course, there is a head. The head is not doing anything, so the head is experiencing drag force on the fluid, and that drag force balances its thrust force, and this whole thing moves on the left-hand side. Okay? So purely through the fact that the drag forces are not isotropic in Stokes' law, you can have a propulsion. Of course, you break time reversal symmetry first, and then utilize the fact that these forces are anisotropic, and that's how you get a thrust by just moving up and down this sort of parallels. Is this clear to everyone? And this story is exactly the same for the helix problem. So if you do the helical problem, and if you think of that there are these two waves on two planes going on, it's identical, and you can show that the forces that you get, the thrust forces you get in that problem is also proportional to the difference in these quantities. Sorry?
In the helical case,
It's a good question. I think it does, but I'm not sure on top of my head. Yeah. So the helix case, the other interesting thing is that you're purely rotating the helix, right? But just purely by rotation, you're getting this translation out of it. And that's also happening purely because the drag forces are anisotropic. So let's do one thought experiment, okay? What happens, of course, I told you this relation, this is what typically is measured in experiments. What if C parallel is greater than C perp? What if this happens? Which direction will this go? Will reverse, right? So this whole thing will be dragged on the right hand side, and that's really counterintuitive now. Yeah, so that's exactly. So that's very counterintuitive, right? That you have a flagella that's beating and generating wave in this direction, and then this whole thing is also moving in that direction. That's absolutely nothing that you would expect. So it turns out that typically, of course, that's not the case, but it turns out that there are certain eukaryotic organisms which have protrusions along the backbone. So they look like this. These are like needle-shaped things that are distributed throughout the backbone. And if you account for the distribution of this sort of needle-shaped object, you can actually reverse this sign. And if you watch those organisms move, they move in the same direction that they propagate their bending waves. So this is absolutely counterintuitive, and it can only come out through a calculation. Okay. So let's spend last few minutes watching movies again. So I had thought that I will do a calculation. So this is really not a calculation in a sense. This is just a demonstration of the fact that if you have drag anisotropy, things can move in fluid by this mechanism. But you can actually do the full calculation and show what is the swimming speed of the object if the wave speed is such and the wave amplitude is such. There is a calculation that we can do. Today there is not enough time to do that. It's a fairly long calculation. So one option is that we can do it next time and then do something else. Or the other option is that I can send you a derivation or send you a note, or I can tell you the result and explain the result and do something else in the next class fresh. So that's up to you. You guys choose, you guys decide what you would like to do. Okay? Fresh, okay. So no more calculations. Okay. Fine. We'll do something else next class.
How comparable is, like, what is the comparison between the wave velocity?
So it turns out that the swimming speed is always less compared to the wave velocity.
How many orders?
How many orders of magnitude? That depends on three things. That depends on what is the amplitude, typically it goes as amplitude squared. Depends on the wavelength of the problem. Okay, so there is a parameter that classifies what if you take this wave, just draw this. So there is a length, and this is a wavelength. So let's call this lambda, the wavelength, and let's call the other length is lambda. So it turns out it depends on the ratio of these guys, and it also depends on the ratio of the drag coefficient. So it depends on a number of parameters. It's hard to quote a number unless you specify all those things, but you can show that it's always less than the swimming speed. So I would say it's like depends on the problem, but if you do the infinite sheet problem, it's typically 0.7, I think, if I remember correctly, but don't quote me on this. I will have to check. We can just check it from the expression, what it comes out. But of course, it's typically lower than that, because in the sort of infinite sheet problem, you're just generating this wave and you're moving forward, but there is no payload. You're not pushing on something. But typically there is a head, right? The head doesn't do anything for propulsion. It just sits there. So it gets to push it. So velocity, of course, decreases further. Okay. So okay, so we'll visit this. First, let me tell you about these guys. So these protrusions that you see over here, these are called mastigonyms, I think. I don't know the pronunciation exactly, but this protrusion can exactly revert this situation and give you C parallel being greater than C parallel. Okay. And while there are not many good experiments that you can look up online, but there are actually a number of simulations that you can look up where people have simulated these objects along the whole flagella, and you see that this whole thing is waving and it's moving in the same direction. It's very odd. So this, what you see over here, is the run and tumble motion of E. coli. So E. coli is again rotating the flagella. So they have this corkscrew thing that they're rotating, and that's with what they're moving. So let me just play this. So you can see rotations in motion. Okay, so I will like to play this bit, but maybe I will just play it from a little backwards, because there was this questions about reversibility. Let's just start from here. Did you guys all watch this film? Okay, so let's get back to this question of the problem that I want to get back to is this one. There is this head and there is just this guy doing this. Why this sort of breaks reversibility? Let's get back to that question. And so you can switch it off. Yeah. So what this does is that there is this, of course, experiment we saw last time, which was the question of reversibility, where you take these containers, put fluids, rotate and rotate back. There was reversible. So what now G.I. Taylor has done, he has put a rigid ring. So it's a rigid object that cannot deform. And intentionally, this segment is sort of open, so you can see how this object is rotating as things move. So, okay, this object, of course, gets rotated, as you can see. Now it comes back to the old position. Okay, so this is again reversible. But what he does now is that he puts a string, a piece of yarn, he calls it, and this is a floppy object. This can deform. So he rotates, and we'll see what's happened. So you don't come back to the same shape because you're now deforming. Okay. So this is one important piece of Stokes' law, is that while the equations are of course linear, I have erased the equations. The equations, it's okay. The equations are linear, and there are no time in the equations. The equations are of course reversible, but you can also break reversibility by deformable object. So that's coming through this sort of, essentially mathematically that comes through boundary conditions of the problem. The boundary conditions of the problem do not remain linear, so you can break reversibility. And that's exactly what's going on in this problem, because as this moves and as this comes down, it experiences different sort of forces, it behaves differently, deforms differently, and as a result, you break time reversibility. The other thing that I wanted to get at is this experiment. So this is this instrument which can just do this. So it's a paddle which just moves up and down, and I think he initially first puts it in water. Okay. So it's demonstration. Okay, now it's in water, and this is exactly how we would imagine it. It swims fine. Okay, but now this is, I think, corn syrup or something very viscous, and it's doing it, and it's just not going anywhere. So this is exactly an illustration of the scallop theorem at the lab scale, where you have this rigid flap just moving left and right, and things are stuck there. Okay, then here's this very nice, okay, it will come soon, okay. Okay, so now it's this, there is a two helix, they're all rotating, and exactly because you have drag anisotropy, which he also demonstrates by a falling rigid rod, doing the same problem that I did, this whole thing starts swimming. So that's exactly how an E. coli, a lab scale E. coli would swim. Okay. So I think this hopefully gives you an idea of swimming and sort of the general principles of propulsion in, you can close it, yeah, in low Reynolds number. So what we'll do next time, I think, is that I will follow something that Akshit did. So Akshit has this very nice thing where he talked first about the logistic model, right? Then he talked about Lotka-Volterra. Then he talked about May instability. So the flavor of these three topics where you do one problem, you do two problem, then you do n problem, right? So we did the one problem today. So which is essentially a one particle problem. Next time we will see what happens if you have a pair interactions. What happens if you have two particles. So we'll spend some time doing it. And then in the last class, we will do n particles. If there are many particles all interacting through the fluid, what comes out of it? That's roughly the plan. Okay? Okay, thank you.